Now let's go back and look at the basic goals of an index. We saw that a tree is going to nicely support all of these operations algorithmically. And then as far as utilizing the disk efficiently, we'd want to use a B tree or a B plus tree. And the only reason we kind of rejected hash tables was because they don't support range queries. But what if you don't want to do range queries? Then a hash table is actually going to be algorithmically better. It's going to be faster insertion, faster deletion, and faster searches for just exactly a certain item. So if you don't want to do range queries, then you can use a hash index. A hash table to implement an index. And the basic principle is you use a hash structure instead of a tree structure, where you still have to keep disk access in mind. So you make page-sized buckets. And then when you're inserting an item into this hash table, you hash it as you normally would. So you take the key, hash it, mod by the number of buckets to figure out which bucket to put it in, and you put it somewhere on that page. So each of these here, these are all pages. So in this example, A and X happened to hash to index 0, P hashed to index 1, and so on. And if you're using a hash index, then you probably also don't really care about order. So these buckets don't necessarily need to be kept sorted. You just kind of put it somewhere in there. And when we run out of room in a page, you have the standard hash table options. You could do some kind of probing. More likely, though, you're just going to do separate chaining. So you have this disk page, and somewhere in that page you have a pointer to the next one. So in this example here, both of these pages make up the bucket number 2. So anything that hashes to index number 2 will go somewhere in there. And you just keep adding pages to the end of that as needed. As this link of pages gets longer and longer, though, it starts to take longer and more disk accesses to find what you're looking for. So if the total hash table gets too full, you might have to rehash at some point. So how would we make a secondary index out of a hash table? So let's just kind of look at some implementation details in terms of putting this into an actual database. It works very similarly to making a secondary index using a tree. Inside of the buckets, we put the search key for the index for the column that we built the index on, and then a pointer to the record in the main index. And in this case, just as in with a tree, the pointer is just the primary key. So if I was searching for something with a value of A in this second column, I hash on A, I come down here and find bucket 0, I find this entry, and then I take that primary key of 5 and go plug it into the primary index and search for 5 within the primary index. And that primary index could be a tree or it could be a hash structure. It doesn't matter. You can look it up either way. So the pros and cons of using a hash index. Pros are constant time insertion, deletion, and lookup rather than logarithmic time. So it's a good option if your database is basically just a map or you're storing key value pairs. The downsides, though, are it does not support range comparisons. So there's no ordering. It doesn't help you with order by. It doesn't help you with find all things that are greater than X and less than Y. And this last one, though, performance degrades if it gets too full. That's actually the most important downside to a hash index. So what happens when a hash table gets too full? Normally you try to keep the load factor less than 50% in a hash table, and that's just needed in order to guarantee constant time operations. So, and what you do if the load factor gets greater than 50% is you rehash. So what about in a database management system where your hash index is like gigabytes or maybe even terabytes? what are the implications of rehashing an index that large? Rehashing requires basically touching every single record. You have to look, you've made the hash table bigger, so picking which index something hashes to changes for every item, so you have to look at every item and rehash it. With data this large, this could take just prohibitively too long. It could take days to rehash a gigantic hash index. So for this reason, hash indexes have very limited utility, and in fact, they are quite rarely used in practice in a relational database. They are useful if the number of items you're putting into the index is well bounded. So if you know the maximum number you'll ever put into it, then you could just make a hash index that has capacity twice that, so you can always keep the load factor less than 50%. Turns out InnoDB, which is the storage engine behind MySQL and MariaDB, it doesn't even support hash indexes. They are supported by the language, so SQL will let you try to create a hash index, and it will just say okay, but not actually do anything, because InnoDB just says, well, they're not that useful, we might as well not even implement them. For a tree index, the pros and cons, so just kind of comparing to a hash. It speeds up range queries, it speeds up equality queries, although not as well as a hash index, but still really good. Logarithmic is much better than linear. It speeds up order by, so if you just want to sort the entire table based on some column, if you have an index on that column, well, it turns out it's already sorted. The leaf nodes of that index already represent a sorted list by that column. And a tree never needs to be rebuilt from scratch. It does need to be updated and maybe rearranged a little bit, but usually those rearrangements are minor as we're inserting and deleting items. The only con is it's logarithmic instead of constant, but still logarithmic is very good.